Welcome to part 10 of Solving Mazes with Reinforcement Learning. In this video, we're going to be covering the Intrinsic Curiosity module, and which is something that's going to give the agent rewards to promote exploration. But first, there are actually a few bugs in the code base. My first take of this video, found a few different issues, stepped back, took some time to solve them, and we're going to go through and implement those fixes now before we go any further, or you're going to not get the results that you're looking for. So, the first one is in your main.py, and that's going to be tau here. Tau actually needs to be 0.005, not 0.95 or 0.99. 0.99 would have inverted that relationship. The next one is going to be over here in agent. And under agent, we are going to go down to the train method. And we're using updates to set the time steps for the writer here. But we're also using updates a little bit further down to determine when we do a soft copy. So what we're not doing anywhere is we are not incrementing that value. So if you look through, here's where we're doing, if updates equals target update interval, modulus 0, soft update, but nowhere are we actually incrementing that value, so it just stays 0 all the time. So we're going to put that right under updates plus equals 1, right under there. So it's going to write all the scalars, and then it's going to go ahead and increment. The third change, and this is something I messed up several videos ago. If we go to buffer.py and go to sample buffer, states and next states both sample from state memory. And next states should sample from next state memory. So this is one that took me a while to catch. It was just a typo, an autofill. But if you return the state memory as both the state and next state memory, the agent has a much harder time learning. So we're going to go over here to runs, and I'm just going to clear these out again. You don't have to, but it helps me. And I'm going to run this and just make sure we don't have any errors. And this should actually start to learn. Even with just vanilla SAC, we should get some good results, or some at least positive results. And it should start to learn some useful behaviors, even just kind of randomly wandering around. So let's go over to our test py and see how it's behaving. Yeah, you can see it kind of wedged itself in a corner. So it's not being very smart, but it is learning something. Even if the something right now is go in this one direction and you sometimes hit the ball. So the next step in our process here, and you can see here we actually found the target 4 out of 10 times, and we're just a little ways into training. So it is learning. It's not learning super effectively. That's what we're going to get into now. So this is what's considered a sparse rewards environment, by which I mean that it only gets a reward when it successfully gets to the end goal. So if you turn on dense rewards, then the environment is going to try to give it rewards as it gets closer to the goal to tell it if it's going in the right direction. But that doesn't really mimic the real world. In the real world, if you wanted to have this do a physical task, you probably don't have a great way of saying, hey, you got halfway to the goal, or you got 1 inch closer to the goal to help teach it. So what it's stuck with is it's stuck sort of wandering or doing random things, and sometimes hitting good results and then eventually learning. And you can see that here. You can see towards the end of training now, it's mostly hitting every time. So we're getting more wins than losses. what we're going to do to solve this, to solve our sparse rewards problem, is we're going to implement an intrinsic curiosity module. So what is intrinsic curiosity? Well, at its core, to make an agent intrinsically curious, you have to add something to the reward term that doesn't rely on the environment, or at least not directly, that makes the agent want to explore more. There are several different ways to do this. We're going to use a pretty simplistic method, and I'll pull up the diagram that I did at the beginning. So we're going to take an input layer in our ICM. We're going to take an input layer that takes state and action. We're going to pass it through a couple of linear layers, and then we're going to get an output. And that output is our predicted next state. We're then going to compare the predicted next state with the actual next state. And if the predicted next state and the actual next state do not match, we're going to take the mean squared error, the difference between the two, and pass that back into the environment or back into the agent as a reward. So what we're effectively going to be doing here is saying the amount of the negative of this prediction. So however bad it is, we're going to take that error and pass it back to the actor and say that that was a good idea. So what this effectively does is, let's say the agent is, running into a wall. Well, the ICM is going to learn after a few times that running into that wall gives you one state, gives you one response. And then the prediction error is going to go down because it's going to be able to predict the results of running into the wall. So if the agent will now get very low rewards for continuing to take that action that it already knows about. If it takes a new action, let's say it goes left instead of forward. Well, now that new action, the ICM is going to not be able to predict that, and it's going to feed that lack of prediction, that prediction error, back in as a reward to the actor. So that's our next step. We're going to go ahead and build out this intrinsic curiosity module. Before you move forward, please take a moment and make sure that your agent is learning in this environment. So, it should at least be getting some results. It may not be perfect results at this point, but after 100 epochs, 100 iterations here, you'll notice I'm getting, 5 so far out of 10. So about 50% success in our very basic, straight hallway type of maze. If you're not seeing that, if it just wanders around or isn't starting to learn, or another way to look at that is if you're not seeing sort of that upward graph, stop, go back, look at your code, make sure that you're getting some learning in this state, because it should be able to master the sort of straight maze without the ICM. And the reason that's important is if you have a bug here, then it's going to become more complex as we bolt on additional code. You should have a working learning algorithm right now, and we're going to add things to help it learn more efficiently. So let's go ahead and start coding out our module here. So we're going to go to model.py, and I'm actually going to call it the predictive model because that is what we're doing. So I'm going to say class predictive model torch.nn.module, and we will do our init method, self num inputs, num actions, hidden dim checkpointer like we did everywhere else, and we'll do checkpoints. Name equals predictive network. All right, and then as usual, we're going to call our super, predictive model, self, init, self.fc1. So starting to define our fully connected layers. Torch.nn.linear, num inputs plus num actions. So in other words, our state space here. Hidden dim, self.fc2 is torch.nn.linear, hidden dim, self.fc3 is torch.nn.linear, hidden dim, num inputs. And then we'll do our checkpoint dir, self.checkpoint dir is checkpoint dir, self.checkpoint file is os.path.join, self.checkpoint dir name equals _ SAC. All right. We'll define our forward method. So def forward, self state action, and we'll say x equals torch.cat, much like we did before with the critic network, state action across dimension 1, x equals f.value, self.fc1, x, so we're just passing our x through the layers, f.value, self.fc2, x, and then we're going to say predicted state is equal to self.fc3 of x. All right, and then we'll return predicted state. All right, and then finally, we're just going to copy these save and load checkpoints files, or methods, sorry. And then we will come over to our agent and look for where we put load checkpoint. And, well, actually we haven't defined them, so we won't need to add it here yet. We'll do that in a few minutes. So let's go ahead and come up, and in our agent init object or init method here, we are going to come down here, and I'm just going to go ahead and comment that we're going to initialize the predictive model, and we'll do self.predictive model equals predictive model, num inputs, action space dot shape 0, hidden size, and then we'll send that to self.device like we did with the others. And then we'll also declare a self.predictive model _ optim, and we're going to make that atom with self.predictive model .parameters, and we will feed in an LR learning rate. And then finally, this is where we're going to use this exploration scaling factor. So we're going to use a self.exploration scaling factor equals exploration scaling factor. And the reason we're using this is we may not want we want to be able to scale this reward up and down a little bit. You know, for some problems, maybe you want a lot of intrinsic curiosity, but maybe for others that would override the rewards provided by the environment, and you might want to scale that back down. In my own testing, the right value for this ended up being right around 1.5, but it's definitely something you should play with and try to, you know, see what you can do with it. So, continuing down here, we are going to go to the update parameters section, and go ahead and right under here, we set predictive model here to do, and set a to do to add one. So we're going to say predicted next state is equal to self.predictive model of state batch and action batch. We will calculate prediction loss, and we're going to say prediction error is f.msc loss. We're taking the mean squared error of predicted next state and next state batch. And then we're going to say prediction error no reduction is f.msc loss predicted next state state batch, and we're going to say reduce equals false. All right, so why are we taking both? The prediction error is the error that we're actually going to use to go and update the prediction model and try to make it better. The prediction error no reduction is the one that we're going to feed in as an intrinsic reward. And if you don't add this reduce equals false, what you end up with is you end up with a model or an output that's going to reduce everything to one value, one total quantity value, and that value would then get added to every single state in the batch, every single reward in the batch. So it doesn't really help if you're giving the entire batch the total prediction error. You want to incentivize certain states that the model is not good at predicting, not just skew them all by what ends up being a fairly random number. So that's what that's there for. We're going to declare scaled intrinsic reward is equal to prediction error no reduction dot mean across dimension 1. This gets it into the right dimension for what we're doing. And then we can say scaled intrinsic reward equals self.exploration scaling factor times torch.reshape scaled intrinsic reward and batch size 1. All right, and then finally we can say augment the reward batch. So we're going to say reward batch equals reward batch plus scaled intrinsic reward. And because those are the same size matrices, they can just be added directly. All right, finally, or not finally, there's a few things to add here. So we're going to go ahead and add the actual updates to the predictive model to help it learn over time. So we're going to say update the predictive model network, and we'll say self.predictive model optim.0grad prediction error dot backward to our backward pass, and self.predictive model optim.step. All right. And then just to make our comments consistent, we'll call this update the policy network. All right. All that looks good. Okay, if updates, all that looks fine. I think the last thing we want to do here is we actually want to return our prediction error. So right after alpha loss dot item, we want to say prediction error dot item. We want to be able to graph that as we go, and then we'll come down here, and in the same way we will say prediction loss And then we'll do writer.add scalar loss. Here, let's just let's keep those together, and we're going to stick it up here. So we'll do loss slash prediction loss. And then obviously we'll feed in prediction loss and updates. All right. So what this should now do is we should have our predictive network, assuming it's all wired up correctly, adding predicted next state and feeding in those extra rewards to encourage the agent to explore things that it has not yet explored. So let's see if I have any typos here. All right, got unexpected keyword argument name. Let's go take a look at that. So that's going to be model line 130, which, by the way, if you haven't used it before, you can just control click into one of these and it's going to take you to the right place. So let's see what we did wrong here. OS path join, self checkpointer versus name plus SAC is what I should put there, because name is not a parameter, it's just part of the value. And we've started learning. So let's see how this does. And with any luck, it should, let's refresh over here. Our blue line here should outpace our orange line a little bit. Now I will say on the super simple environment, it is not always immediately better, but that's okay. It's not throwing any errors, nothing's failing. We are getting our prediction loss here. And remember, when you look at this prediction loss graph, what you're seeing is how much of a reward it's feeding back to that reward batch. So this prediction loss is not a bad thing. This is basically just telling you that it's giving it some additional rewards in the environment. And here, I feel like this probably proves our point pretty well. So if I zoom out on this, let's expand. There we go. That's a little better. So you can already see that we went up, pretty quickly right off the bat there. I mean, we're already, sure, it's going to dip back down, but you can see we're already starting to learn in general more quickly than we did with vanilla SAC, even if it's bouncing around a little bit. All right, so I think that is probably a good enough mini demonstration on a simple environment. What about curriculum learning? Because that's one of the things that was promised in the beginning of this video series. So curriculum learning is basically just handing the agent increasingly more complex environments and using a simpler environment to build up to a more complicated one. So in this scenario, we want the agent to understand things like getting to the goal is good. And out of the gate, it really doesn't. It's got no rewards. It has no idea what it's doing. It is just randomly flailing around trying things. So if you take it and you drop it in a more complex environment, a bigger maze, it's going to take a long time just to understand the basics that there is a reward point that it can get to that's going to give it some kind of reward signal. And it'll do it eventually. The intrinsic curiosity capability will help you there, and it'll help you find, it'll help you find your some reward signal. And you can see here, like where this ended, our new code did perform better than our old, even if just a little bit. But yeah, you don't, if you can help it, you don't want to throw it in a more complex environment right away. So what curriculum learning helps you do is stair step through a curriculum to get to something a little bit more complicated. So what we're going to do, and the cool thing is since we've handled all this in functions under the agent method, we can actually just do a little bit of copy and paste, and that's going to be enough to set up our second phase. So I'm actually going to copy the large maze over from my original code base. I will paste this down in the video description. I don't expect you to faithfully copy and paste all these zeros and ones. We're going to start, we'll say, we'll need to change a couple things. Instead of max episode steps, we're going to do phase 2 equals 500. And then here, we're just going to copy the gym.make code down. We'll just redefine the env variable. And we don't need to make any changes here. Well, actually we do. Hang on. We need to change straight maze to large maze. And then really, at that point, we will just do another round of agent.train. And then I think we've already, and at the very end, just for cleanness, we'll do env.close. And that really should be it. So at this point, well, we'll do a couple things to make it easier to see. So up here, summary writer name, we'll do this, we'll call this phase 1. And then we'll call this phase 2. So what we're doing effectively is we've declared our agent, we've declared our memory at this point. We're going to keep the memory, we're going to keep the agent, and we're going to train the agent for 100 episodes. We'll do our large maze, we'll do our max episode steps for phase 2, and we actually do need to pass that in. Okay, there we go. A few more changes than I thought. We'll do max episode steps for phase 2. We'll add that here and here. And then we'll make episodes equal, we never declared episodes up here, so that's fine. We're just going to make this, let's do 3,000. 3,000 is probably pretty good to start to get a view of how well it's going to go. And then let's run it and see if we run into any problems. So it's going to run through, actually, you know what? Let's make do one more thing. I'm going to go and clear out runs here, just so I can get fresh data. And we'll run that again. So now it's going to go through step 1, and it'll do that for 100 epochs. While we're doing that, let's go ahead and move our test pi over to the same large maze that we're using in main, and I'll pass that in here. And this is going to run the same model that's currently running on the straight maze, of course. The whole point is to build an agent that can solve, multiple different environments. And you can actually see that it's already finding some success. It's already, as long as it can go in one of its normal directions, and that gets it close to the ball, it at least starts off at this point knowing that that goal is good. It's just not very intelligent about getting there yet. So here we're through episode 40. I'm going to hit pause on the video and come back once we hit a little further in training. All right, so we can see now that we did get into our second phase of training. It's going to take this quite a while at this point. So, it could take 3,000 to 5,000 episodes to really get good. And because we're doing 500 steps per episode instead of 100 steps per episode, it will take it a little bit longer to, run each simulation. It's not like it's just going to fail really quickly. But you can see even here, we've already started to get some positive results. Those 3 runs were fairly successful. So I'm going to go ahead and run it, and we'll just see what it's doing right now. So as long as there's a kind of clear path to the goal, it can wander around and try to get closer to it. And if it's of any interest, it really can't see the maze, so to speak. It's not like it's looking at it from a top-down view. The state space is basically its current position and the position of the goal. And it's trying to figure out how to get there. So I think this is a really good place to stop the video and just let this train for a while. If you're following along, you should have an agent that's capable of learning and is starting to make some progress. You should be starting to see it attempt to hit its objectives. When this finishes in several hours, I will come back and post the final video and show you my results, any tweaks I have to make along the way, and we'll close this out with some next steps for you.